Okay, we're going to begin looking for the last pair of derivatives of inverse trig functions, and that is the derivative of the secant inverse and the derivative of the cosecant inverse. We'll start with the secant inverse, and whatever that comes out to be, the derivative of the cosecant inverse of x will just be the opposite of that. So we start with y is equal to secant inverse of x, and we can rewrite that as, recalling once again that with an inverse trig function, we give it, if we're looking for the inverse trig of secant, we give it a secant and it gives us back the angle. So in this case, y is the angle and x is the secant. So y is the angle whose secant is x, and we write it as x equals secant y. We're going to take the derivative of both sides with respect to x and differentiate implicitly. Okay, and when we do that, we're going to get 1 on the left side, and the derivative of secant of y, if you recall, is secant y tangent y, and then we're going to have to multiply that by y prime because we're not differentiating with respect to y. And once again, when we solve for y prime, we're going to get 1 over secant y times tan y. And of course, we go back to our triangle. We state that y is the angle whose secant is x. Y is the angle. Secant is if cosine is adjacent over hypotenuse, then secant is going to be hypotenuse over adjacent. And so if the hypotenuse over adjacent is x, we'll get x and 1 for that. Now, we will need to find the other side using the Pythagorean theorem, and that is just the square root of x squared minus 1. Alright, so we're looking for the secant of y. Well, the secant of y, again, is the hypotenuse over the adjacent, so that is just x. And then we need the tangent of y, and tangent is the opposite over the adjacent, so that is square root of x squared minus 1. Okay, then there is one little twist to this problem, and to understand this we're going to have to actually go and look at the secant inverse function. And we'll step over to WinPlot for a second. And we begin by looking at a graph of the cosine function. So what you see here is a graph of the cosine function. And then we plot the secant function on top of that. Basically, wherever the cosine is 0, we're going to have asymptotes for the secant function. And wherever cosine has a min or max, we're going to get little saddles riding on top of them, or U-shapes facing up and facing down wherever there's a min and a max. I'll add that on at this point. And so the graphs that you see in the reddish color there is the graph of the secant function. And I say that the secant rides piggyback on the cosine. So you draw the cosine, and wherever you have the mins and maxes, you draw the right side up and the upside down u's. Wherever cosine is 0, you're going to have asymptotes for the secant function. Now, if you recall that in order to have an inverse function, we must have a function that is one-to-one. It has to pass both the vertical line test and the horizontal line test. Well, the secant function passes the vertical line test, but it doesn't pass the horizontal line test. So we're going to have to limit or restrict our domain. So first I'm going to get rid of the cosine function, and then I'm going to show the restricted domain of the inverse secant function so that we can find its inverse. And that restricted domain is from x equals 0 to x equal pi, and you can see that function there. Now, what we need is to reflect this about the line y equals x, which is the line in light blue there. And when we reflect that, we get the line that is in dark blue there. Now, one thing that you should notice about that is that this does have x and y values. It's not defined for all x values. But you should note that the slopes on both of those dark blue lines are all positive. And so the derivative must be always positive. And so we're going to go back to the original screen. And if you notice in the denominator we have square root, that will always be positive, but the x value could be negative when x is negative. And we need to force that to become positive by making that absolute value of x. And we have our final two formulas.